Hi everyone, this is Kyle with Image Expert, and in this course we are going to discuss how to optimize waveforms. To get started, let's cover what is a waveform and how are they used in the industrial inkjet process. Here's a diagram of what's going on inside the printhead. The waveform is an electrical signal that's sent to each of the nozzles inside the printhead. The nozzles are made out of a material that moves when an electrical signal is applied. As you can see, when voltage is applied, in this particular case, the back of the nozzle is moving. When the nozzle expands, it draws ink in, and when the nozzle contracts, it jets out a drop. And this process is repeating thousands of times per second to form the jetting that we know inside the process. So we're going to focus on the electrical signal in this course today. Depending on the design of the printhead and which manufacturer it comes from, the waveform can take a couple of different shapes. So there are some versions of the waveform where it is an active high, so voltage is applied in the positive direction, which causes the nozzle to move. There are also versions of waveforms where the printhead sits idle at a voltage and a drop in voltage is what's causing the walls of the nozzle to move. And then there are some printheads that are a little bit of both, where they can move in the negative or the positive direction. Regardless of which printhead you're using, they all follow the same fundamental waveform optimization techniques, and those are what we're going to cover today. Before we get into the details, a good thing to understand is, why do we care? Why does this really matter, and what is this going to do for us as inkjet developers? So the printhead manufacturer often recommends a waveform for their head that performs well under most circumstances. And that's a great place to start if you're just looking to jet and see how your ink performs or see what the process looks like. If you've got an abnormal ink, you might find that the recommended waveform really doesn't perform well and you've got to explore changing it. Or if you've got an application that's really demanding, you've got to optimize every aspect of the system, and maybe jetting well isn't good enough and you've got to jet perfectly. And that's where looking into making improvements to the waveform could help. Some of the improvements that people are most often looking to make through waveform changes are changing the drop volume, increasing the speed of the drops, reducing any satellite formation, or improving the overall stability of the jetting. And these are all things that can be accomplished through optimizing the waveform. The basic parameters that we're working with for a given waveform is the voltage or the amplitude of each individual pulse, how long that voltage is applied for, which is known as either the pulse width or the hold time, depending on the manufacturer. And if you're doing grayscale printing, where there's multiple pulses involved, the spacing between those pulses is another factor. And we'll go through how to make changes to all three of these and what's the process you can follow. To start with, it's important to kind of define what the goal is of your jetting. Every application is a little bit different. To kind of demonstrate this, we can ask ourselves, we'll take a look at two waveforms and we'll try to figure out which waveform is better. One waveform, waveform A, we can see does not have any satellite formation at all throughout the entire drop formation, whereas waveform B does have some satellites. So depending on our application, waveform A or waveform B might be better, and some applications would tend to go towards A and some would go towards B. Here's why. If we take a look at what the actual printing looks like for those two waveforms, we can see that waveform A is a little bit less consistent. So the edges are a little bit more ragged, whereas B, the lines are a bit more well defined. The thing about A versus B, and we'll go back to these waveforms, is not only does the satellites matter, but the speed of the drop also matters. In some applications, having a higher speed is better, and you can actually sacrifice some of the satellites, and more satellites are acceptable. An example like this would be textiles, where you're trying to throw the droplets of ink a really far distance because the print heads tend to have a pretty large standoff. So in an application like that, high velocity of drops trumps perfect drop formation without any satellites. Something like printed electronics would be the inverse. The print heads can normally be very, very close, so the velocity is not as important as making sure there are no extra drops of conductive material traveling anywhere else that they're not supposed to be. So we were talking about where do we get started. We want to define our goal. And our goal for our waveform kind of breaks down to these 5 criteria. So how many satellites are acceptable for our particular application, both in terms of the number of the satellites and then also the size of the satellites. The volume of the drop, the velocity of the drop. Again, each application kind of has an acceptable range of throw distances, and so we need to establish how far from the print head do these drops matter. And then the speed / frequency / resolution. All 3 of these things are tied together. But this is the speed of your printing process. So how fast is your printer need to operate to be able to do your application well? So all of these things are things that we're going to take into consideration for how to optimize a waveform to kind of set our goal. And it's okay if in the beginning you actually don't know the answer to all of these things. Most often you won't, and you'll have to do some printing before you can really decide how to balance all of these things. So what we did for our particular setup is we have a drop watcher and a sample printer. So we took a look at the jetting on the drop watcher side, and then we took a look at the resulting sample print. And what we can do is we can see the drop watching and the resulting print, and it really ties together criteria like how does the velocity impact the print? How do the number of satellites impact the print? So that's the system that we used here throughout much of this process. To get started, we're going to use the printhead manufacturer's recommended single pulse waveform. Most printhead manufacturers kind of define this in the user manual for the head. They outline how to make something like this and what it looks like. In the case that the printhead manufacturer doesn't show it in the user manual, quite often you'll be able to either from your printer provider or the printhead manufacturer themselves, they'll be able to just send you a waveform. And you can use that to get started. So what we'll do is we're just going to scale the voltage of that waveform up and down to experiment with different balances of drop speed and the number of satellites. So the higher the amplitude of the waveform, the higher the speed of the drops will be. And it quite often tends to be the higher the number of satellites. Most print heads allow you to simply scale a waveform without making any other modifications to it. So we'll just scale a default waveform through a bunch of different voltages and just take a look and see what happens. So here's an example of an image where each different slice of the image uses a different voltage scaling. So the lowest voltage is over on the left, the highest voltage is over on the right. So we test a bunch of different waveforms with different voltages and take a look at the jetting. This was captured on a Ricoh Gen 5 printhead, and it uses GIS drive electronics. One thing that's nice about the GIS drivers is that they allow you to send commands to the drive electronics through software. to change parameters of the waveform. So for example, we can create a list of voltages that we want to test and automatically send them to the GIS drive electronics, and it's going to change the waveform automatically. So creating an image like this only takes a couple of seconds because we've got the software all tied together between the drive electronics and the drop watcher to change the waveform, capture an image, make a change to the waveform for the next voltage, capture another image, and put all those together. So we use that functionality within GIS a couple of times throughout this course, but that's just to give you a little background on how we're generating this image. So what we can see is that as the voltage increases, so does the speed of the drop. Each of these slices is taken at the same moment in time. So we can see on the slower end of the voltage, we've got our distance from the print head on the left here. The drop hasn't even traveled 0.5 millimeter, whereas at the same moment in time on the higher voltage, the drop is almost 1 millimeter from the head. So the drop velocity is definitely increasing as we increase that voltage. You can also clearly see that the number of satellites is increasing. And again, based on the application, one of these is going to be better than the other. And we have to decide where's the right balance between the two of those. And the way that we're going to do that is by actually printing our images. So we see what the drops look like here. We're going to take kind of a representative sampling. So maybe this waveform, and this waveform. And we're going to actually print a sample image and we'll compare. So we're looking at things like how straight are the lines, like we were before. Looking at things like, is the ink bleeding? And then also looking at things like, is there any satellites that are present, or how does the shape of the drops compare? And depending on the distance from the print head to the substrate, how fast your substrate's moving, all these different things that are somewhat unique to your application, those are going to help decide what's the right balance between speed and clean drop formation. So we'll take this test and kind of put it in the back of our minds of, what are we looking for here? Is a higher speed more acceptable, or higher satellite count, or do we need to be slower with fewer satellites? To get started with the actual optimization, we're going to bring that voltage back down to the point where we get a controlled jetting of a nice looking drop with limited satellites. Usually with just about any waveform in ink, you can lower the voltage enough to get to this level. So with the print head here, this is a Dymatics Samba drop that we're using from here on out. So we've lowered the voltage to the point where we've got no satellites. So this is a double pulse, again, for measuring the velocity. So there's actually no satellites here. And we've got a velocity of about 5 meters per second. So for some applications, this velocity might be a little bit slow, but again, this is just going to be our starting point for the optimization. The next step is we are going to sweep through different values of the pulse width. So again, the pulse width is how long we are applying a voltage for. And we're going to find which value of that pulse width yields the maximum drop volume and velocity. In general, the pulse width tends to be quadratically related to those velocity and volumes. So there is going to be an optimum pulse width that we can find based on this test. To kind of explain why that is, I put together a diagram here. So each of these slices is the nozzle, and we're just looking at what's happening to the nozzle over time. So when the voltage is applied, the nozzle, the back wall of the nozzle chamber moves. and that creates a pressure, right? So as we're applying voltage, the wall moves more and more and more, and then when we back that voltage off, the wall goes back to the way it was originally, its idle state. This is what's happening with that waveform pulse, and the duration of that this occurs over is our pulse width. So the wall's moving, and it creates a pressure based on the movement of that wall. Here's what's happening to the ink. So when the wall moves, the wall creates a pressure on the space inside the nozzle. And when the wall is retracting, it's creating a negative pressure on that space. The nozzle is full of ink, so in addition to the pressure of the wall, the ink is actually going to start moving in the nozzle as well. It takes time for the ink, the wave of pressure to pass through the ink and out the nozzle where it's going to jet. So with a properly optimized waveform, we notice that the pressure from the nozzle and the movement of the ink are always in the same direction, right? So as the nozzle, as the wall of the nozzle is closing the nozzle, it's pushing in, the ink is moving away. When the nozzle wall is returning back to its original position, the ink has moved forward, bounces off the other wall, and is returning backwards. So our pressures and our motion always line up. So here we can take a look at what happens if the pulse width is not optimized. So if the amount of time that the wall is moving does not align well with the motion of the ink, this is what's going to happen. So as you can see, we're closing the wall of the nozzle, and then we are opening it again, and here's our new pulse width, how long it takes that to occur. The amount of time that it takes for the pressure to propagate through the ink remains the same. This is a function of the speed of sound of your particular ink. So the ink, the movement of the pressure in the ink is going to remain the same as before. So what you'll notice is there are several instances where the ink is moving in one direction and the wall of the nozzle is moving in the other. So you've got pressures that are trying to fight against each other. Here's a great case. So the ink is moving backwards because it's bounced off the wall and is going backwards, but the back wall of the nozzle has now started its next cycle and is pushing forward. So we've got the wall pushing in one direction and the ink moving in the other direction, and they're kind of canceling each other out. For a waveform, for jetting, this is not ideal because it's wasted energy, and B, it can kind of cause unstable motion within this nozzle. You want it to be a nice rhythm. So this is why we're trying to optimize our pulse width. Every ink is going to move a little bit differently. So we have to figure out what's our pulse width to match the movement of that ink. So here we go, back to our jetting. We tested a bunch of different pulse widths. And we captured an image of the drop, again, at the same moment in time. And each slice is a different pulse width. And we can see that the velocity of this drop is peaked somewhere around this position. Again, the closer the drop is to the nozzle, the slower it's going because we're taking this picture at the same moment in time each time. So we measure the velocity of the drop. You can either do it by eye or using the drop watcher. You can get the actual data. But we want to find the pulse width that yields the maximum velocity. That means the pressure of the wall and the pressure of the movement of the ink are going in the same direction. So when they are perfectly in sync, that's going to yield the fastest drop. So that's what we're looking for. And we're going to determine what that pulse width is. In this case, we've got our list of pulse widths that we tested down here. So I think it's about 2.1 or 2.2. So we've taken our optimal pulse width And the next step in our waveform optimization, once we found that pulse width, is to adjust the voltage or the amplitude of that pulse. Generally, there's a linear relationship, as we saw before, between the voltage and the drop volume. The higher the voltage, the faster the drop goes, but there's also an increased number of satellites. So, again, we'll do a sweep through different voltages for that pulse and examine the results. As we saw before with the Rico head, we've got the lowest drop velocity at the lowest amplitude. And as the amplitude increases, so does the velocity. Based on the testing we did before, we should have an idea of whether or not satellites are acceptable, or what sort of velocity we need to do to get a good print. So we're going to take a look at which voltage that we've just generated aligns best with what that testing of what our original goal was. And we'll pick that voltage and continue forward. So if we wanted a drop that was fast but did not have satellites, we would maybe use this voltage to continue forward in the optimization process. The next step is that we want to ensure that this waveform that we just created is going to work well at a bunch of different jetting speeds. Most printers, or most companies that are making ink, they want their ink to perform well whether you're printing slow or whether you're printing fast. And so it's important to test your ink at a bunch of different jetting frequencies. Using the same process that we did before with the GIS drive electronics and automatically changing the voltage or the pulse width, we're also able to change the jetting frequency. So in this slice, each slice of the image is a different frequency. This slice is 1 kilohertz jetting all the way up to 30 kilohertz. What we're looking for is to determine if the jetting is consistent across this entire range. So we're looking at the velocity of this drop over time, whether there's any satellites, whether the jetting gets out of control or the nozzle stops firing. In this case, it looks pretty good. If the results were not good, we would go back a step and try a little bit lower of a voltage. To give an example of what the results not being good looks like, here's an example. So here is a Dymatic Starfire printhead, and we are jetting at 1 kilohertz. And you can see in this image that there's a little bit of meniscus activity after the drop is fired. We'll talk about what's happening in the next slide. So now we're going to increase to 5 kilohertz. So there's 5,000 drops a second now, and we start to see a little bit more of a buildup around the nozzles. In a second, we're going to go to 10 kilohertz. At 10 kilohertz, we start to see wetting, and even wetting to the point where it's causing the nozzles to stop firing. So this would be an example of where a waveform might work perfectly well at 1 kilohertz, but not at 10. And let's talk about why that happens. If we go back to our diagram of what's happening inside the nozzle, we've got our optimized pulse width so that the movement of the back wall always matches the movement of the ink. This is repeating thousands of times per second. So this is one drop, and then we wait a certain amount of time, and then we jet our next drop. The movement of the ink, it's kind of residual. It doesn't immediately stop moving inside the nozzle when the wall does. So it takes a little bit of time for the movement of that ink to die down. When you're at a low frequency, there's plenty of this time for the ink to stop moving before the next drop happens. At a higher frequency, that might not be the case. This second drop is coming much faster because we're at a higher frequency, and maybe the movement of the first drop has not completely settled yet. What happens is we've got this drop, the ink is still moving, and we've added another pulse to it. So now it has even more momentum than what it originally did. What this looks like is the drops are actually going to be even faster than normal because you've got the momentum of the wall plus the momentum of the ink plus the residual momentum of the ink from the firing before. So all of these things added together yields extra strong jetting. What this looks like in practice is we can see here that at certain frequencies the velocity of this drop really picks up. And that's what happens when the resonance of the jetting from before is adding on to the current drop, and it's increasing the momentum. And the jetting, as you can see, the velocity is much faster, there's satellites, and the stability goes down. So by adjusting and looking through all those different frequencies, this is what we're looking for. Are there any sections or any speeds where the jetting would be unstable for that particular waveform? And if it is, we have to decide whether or not this is acceptable because it's not at a printing speed that we would be using. Or if it is, we would have to go take back a step and try a different voltage or even a different pulse width to try to adjust when this occurs. If you are printing grayscale, which is multiple pulses that combine together and form multiple different drop sizes, or if the drop volume and velocity of the single pulse isn't high enough for your application, you might have to use multiple pulses to form a drop. To start the optimization process for that, we're going to duplicate the optimized pulse that we just created. So we're going to take the same pulse width, the same voltage, and we're going to duplicate it to make a 2-pulse waveform. The step that we're going to do here is we're going to adjust the spacing between these 2 pulses to figure out what is the ideal spacing until the drop volume and velocity of the resulting drop is maximized. A word that's commonly thrown around in Inkjet is we're trying to determine what the acoustic time of the printhead is. So how long does it take for that ink to move from the back of the nozzle to the front and to the back? What amount of time does that take? So that way we can ensure that we're timing our pulses correctly. Here is a look at the jetting. And you can see that after the drop is fired, we can see that residual movement of the ink still in the nozzles, right? We could see it come out, it moves all the way back, we can see it come out again. This is that residual momentum inside the nozzle. And we want to understand by looking at how long does it take between these pulses, how long does it take for the ink to move back and forth inside that nozzle. If we go back and test a bunch of different spacings between those pulses, we generate an image like this. So we've tested a bunch of different pulse spacings, and we can see that the velocity of the second drop, so the drop formed by that second pulse, where is it maximized? And it looks like it's maximized somewhere around here. The velocity of that second drop is going to be maximized when we've spaced those 2 pulses out appropriately so that the momentum of the first is not fighting the momentum of the second. So when they're perfectly optimized, that's when that drop is going to have the highest velocity. And so this is our pulse spacing. That pulse spacing is going to be consistent because that's dependent on your ink and it's dependent on the head. So for a given ink, you can use that same timing and create as many pulses as you need with the same timing between them, essentially. So you can create a multiple pulse waveform using that technique. Once we've gone through testing a bunch of different pulse widths, adjusting the voltage, testing all the different frequencies to ensure that the jetting is consistent across a bunch of different speeds, if needed, adding that second pulse and adjusting the spacing between them. Once we followed that step and got into this level, we're pretty well optimized. And it might only take a little bit of fine tuning to get to that perfect level, but this will get you most of the way there. If you have any questions at all about the waveform optimization process, or would like to see what this looks like live with a print head and a drop washer and a printer, feel free to reach out to us at info@imageexpert.com or contact any of the applications engineers at ImageExpert, and we would be happy to help show you that. I hope you've learned something and enjoyed the presentation, and thanks a lot.